The Complete Classification of Solids is a General Chemistry 2 lecture, so we're going to skim over most of the learning outcomes and focus on the ones emphasized in blue so we can understand the three main types of bonds formed. Specifically, we want to highlight the differences between ionic compounds, covered in section 9.4, covalent compounds, covered in section 10.1, and metallic bonding, which is touched on several times throughout general chemistry. Let's begin. The first step in classifying the crystalline solids is to determine if they are made of molecules, ions, or atoms. Next, we need to think about how these components are held together in the solid, both on the intramolecular level, think bond type here, and the intermolecular level, which we'll say for Gen Chem 2. As the name implies, molecular solids are made of molecules which are held together in the solid by relatively weak intermolecular forces that are easily disrupted by adding low amounts of heat. Think about ice, for example, which melts at 0 degrees Celsius. What about some other examples? Dry ice, or solid carbon dioxide, is a molecular solid, as is sulfur dioxide and benzene, C6H6. While these three examples are recognizable as molecules, that is, nonmetal atoms sharing electrons and covalent bonds, we see too that there are some elemental examples we need to consider. For example, we know that there are 7 diatomic elements, including iodine, and there are elements that have several allotropes or different physical forms in which the element can exist. Sulfur typically forms long chains and S8 rings, as shown here, while phosphorus can form separate tetrahedral molecules, which are known as white phosphorus, or it can form linked tetrahedra, known as red phosphorus. Our next category of crystalline solids are the ionic solids. Recall that ionic compounds result from the complete transfer of electrons from metals to the nonmetals in a compound. For this reason, we cannot call ionic compounds molecules, but rather we talk about them as formula units. Since ionic bonds are much stronger than the weak intermolecular forces that hold molecular solids together, we see that ionic solids have much higher melting points. Think, for example, of table salt, or sodium chloride, which has a melting point of 801 degrees Celsius. Zinc blende melts at 1,185 degrees Celsius, while cesium chloride melts at 645 degrees Celsius. These high melting points reflect the large amounts of energy needed to break bonds, a topic we will cover later in Chapter 10. Our last category of crystalline solids are made up of atoms. This category is subdivided by the type of atomic unit that makes up the solid, since the three types exhibit very different inter- and intramolecular forces. While we'll discuss non-bonding atomic and metallic solids now, we'll hold the subject of network covalent solids for Gen Chem 2. The non-bonding atomic solids are made up entirely of non-metal atoms held together by the weakest type of intermolecular forces, resulting in very low melting points. For example, the non-bonding atomic solids are easy to spot because they are always frozen noble gas atoms. That's it. Nothing else qualifies. Our next category of atomic solids are made up entirely of metal atoms. Metals are unique in that they possess non-directional metallic bonds, which means that you can think of the metal nuclei as being surrounded by a sea of electrons shared between them. This leads to the unique properties found in metals, including their ability to conduct heat and electricity, to be drawn into thin wires, ductile, and to be hammered into sheets, malleable. The only property you can't rely on to help you characterize metallic solids are the melting points, which tend to vary quite a bit. This is especially true when you consider that mercury is a liquid at room temperature, while gallium is a solid that can melt just from the heat of your hand. What about some other metals? Copper, iridium, and zinc all crystallize into structures that look a lot like the ionic crystal lattices we've seen so far. Keep in mind, though, that the electron sea surrounding the nuclei give metals their unique properties. To summarize, when classifying crystalline solids, the first question you need to ask is this: is the solid made of molecules, ions, or atoms? I'd like to offer up this decision tree to help you characterize the crystalline solids. If the solid looks like it is made of a molecule, it could be a molecular solid or a network covalent solid. Molecular solids are held together with dispersion forces, which results in very low melting points, such as frozen methane, CH4. Ionic solids are made up of ionic compounds, a metal and a nonmetal, while atomic solids made of frozen noble gases make up our non-bonding atomic solids. Finally, atomic solids made entirely of metal atoms are classified as metallic atomic solids.